Okay, we're going to start with the second part of the discussion session now. So the first, let's start backwards again. Who is in room 4? Who is the speaker for room 4? Are they all?
Brian, speaker for room 4.
Are we presenting?
Oh yeah.
Now?
Oh yeah.
Okay.
You're speaker for room 4. You're in.
Okay. Yeah. Right now? Okay. So what do I do with the mic?
Come up to the mic in the front. Yeah. Present what you learned, I guess. You can use that mic or this mic.
Okay. Okay. So there are. Oh yeah. Sure. So me and Julie are going to teamwork on this. So there are several issues that we discussed. So we had this kind of large scale, small scale, bridging that gap, and also the observations versus simulation. So here we are, an observer and a simulator. So generally important, we thought, how comparable are observations to simulations? Synthetic, using synthetic observations, there's a lot more of that going on in the last 5 to 10 years. How informative are observations of single and specific objects? Or how good are the physical models and simulations? These are kind of questions that we were thinking about.
Thank you. Yeah, just having, in observations, we look at one object very deeply, but how does it generalize to the more general population? So that was something that we discussed.
We also were thinking about black hole feedback across galaxy mass, right? This is very important. Galaxies like in the dwarf regime versus in the cluster regime, and then in between in intermediate mass scales, isolated versus group. These are very different environments in which black holes interact with their environments in. Clusters are an obvious case. They've been studied since the 70s, and you can really see the impact on of AGN feedback. It's a lot more visible. So the question is, like, can we probe AGN feedback galaxy by galaxy in these lower mass systems? How can we do that? We don't have links yet. There's other things coming out. LEM we heard about. Because we think that also, we talked about the CGM fraction being really important, because in models, they really differ from model to model. And observations have difficulty finding constraints for these kind of intermediate mass cases.
Yeah, if I can add to that, so if we want to measure the CGM fraction, which would be great to distinguish between models, currently it's really difficult to do that. If we have, LEM is a telescope that is being proposed. It's an X-ray telescope, and it's really designed it'll be able to map the CGM in galaxies. So we would be able to spatially resolve the CGM in many galaxies. So that could be a way of testing this.
Yes. Another problem is not just the mass scale, but also time and across time. So how is feedback important across time? AGN and high redshift galaxies are very different from AGN and low redshift galaxies. And of course, their environments are different. A Milky Way mass galaxy today is very different from a Milky Way galaxy at redshift 2 or even at 6. And so thinking about how black holes affect galaxies across cosmological time is really important as well. And then similarly with time, thinking about time scale at which feedback affects matter. So you're thinking about disk properties. It's very quick. We saw that in the very first talk, the timescales for the disk versus the timescales for the torus, but also the timescales for the halo, and how energy is transferred from these jets versus these winds. We want to understand that too. Okay, and then also Thinking about how some simulations use black hole feedback to get the right galaxy properties. And we don't really care about, sometimes about the feedback that we actually employ. We want to just get the galaxy properties right. Versus thinking about the black hole properties and trying to get that really correct and not really caring about the galaxy properties themselves in more individual simulations. So we've seen various talks that do one or the other sometimes, and we want to think about, how can we get all of this right? How can we start to try and push towards a model for black hole accretion and feedback while also getting galaxy properties correct? And this might be, due to maybe the mismatch between getting these properties right at later redshifts. Does it matter if we do it at early redshifts or not? And I think there's more needed communication between, the galaxy and the black hole communities.
Yeah, we can go on with the solution.
Sure.
Okay. Okay. So now that we've spoken about all these difficulties, these challenges, we have two solutions that we'd like to propose. So the first one is really, as an observer, having a multi-wavelength view, not only because it teaches you about the different phases, but also you can use, for example, X-rays to probe really near the black hole, what's happening in the inner parts of the accretion disk. UV will be a little larger, infrared might be the torus, really starting to think about the whole time scale and how it affects the galaxy in real time. So that could be a solution for that. And do you want to mention the second one?
So the second one is kind of the idea that simulators and observers kind of should use, should sit together and try to figure out how to break these degeneracies. So one thing that is personally something that I really want to do is use these observations of, for example, H alpha outflows from black hole feedback that we see in these galaxies at kiloparsec scales. And you're only really seeing a few % of the actual outflow in H alpha, right? But how can you actually use simulations to help you think about what is happening in the other phases? And then how can you actually test that with multi-wavelength observations, right? And so thinking about simulators and observers sitting together and trying to solve this problem and get better constraints on our models, because we're using, different velocities and different mass loading factors. And it's kind of they're all free parameters that we're not really sure how to constrain.
And on that note, we have a proposition for you. So, one of the questions that we talked about was, what are all the simulations currently being done for AGN feedback? What are the pros and cons of each of them? As an observer, I have, I remember the names, but I don't understand in detail, what's the difference between different simulations. Even simulators, they said as well that it's difficult for them, to know other simulations they haven't worked on. So we created a channel on Slack, which is called a list of simulations. And we invite each and every one of you, if you are working on simulations of AGN feedback, what we would like you to enter in that channel is the name of the simulation, maybe a reference paper, like one of the first papers on the simulation, and a list of pros and cons that, according to you as an expert of that simulation, what are the pros and cons of that? And with that, the idea would be to kind of make a list. I'm thinking maybe like a figure that summarizes all of that, that we can then share with everybody.
We ask the modelers and simulators to be vulnerable and put down their weaknesses as well. Because that's very important. We all have weaknesses.
Yeah, great. Are there any questions for this group at all, or and does anybody at all want to add anything to this discussion? I think it's a really good idea to do that. I like that a lot. Does anybody? Nope. Yeah. Over here.
I have a thought that's kind of related to connecting the simulations with the observations. So maybe I just misunderstood, but I feel like we heard in your quick talk today about how you are finding nearly maximal spins, right? For or a majority have maximal spins for the supermassive black holes.
Well, thank you. For the sample of 100 FR2 sources, which are like the brightest 3CR sources, 2/3 of them were maximally spinning, but the remaining 1/3 had a very broad distribution of spin values. I don't think it's surprising that, things with the most powerful jets in the universe should be maximally spinning. That wasn't surprising, but it was a little surprising how many sources had low spins. So I think in the work that I presented, there was a selection effect that we're sort of selecting sources that we anticipate will have high spins. And other studies where I have the paper with 750 supermassive black hole spins, there's lots of sources with low spins.
Yeah, I just think my question is how that relates to the MAD picture that we were talking about earlier today, right? Where I think it was, you said that, right, with this MAD picture, they get spun, like the supermassive black holes are being spun down, right? And that the energy is, again, correct me if I misunderstood, going to the jets, which actually just seems like a contrast.
It's the same thing.
Is it the same thing?
Well, if I may say something, I think often in the MAD talks, people sort of separate things into high accretion rate and low accretion rate. And I have found no dependence on accretion rate whatsoever. I have sources with all the way from 10 to the -6 L Eddington bolometric luminosities up to L Eddington. And all the relationships are completely in log space linear. There are no features in any of the distributions, all the relationships. And I don't see any difference at all in the relationships between the very bright FR2 sources and very, very weak liners. So I'm not sure if it's just that all of these sources have the same process and they're all MAD, even, well, as the acronym, MAD. But it doesn't seem to have anything to do with the bolometric luminosity of the disk and Eddington units.
Yeah, so just to piggyback off of that, we believe that it's possible to be MAD both at the very low Eddington rate regime and then also in the Eddington to super Eddington regime. And potentially it's only in this thin disk regime where you wouldn't have any jet to do this kind of measurement with, that you would end up not MAD. One thing that you may have been thinking of is that it seems like all of these maximal spins might be inconsistent with the picture where things are spinning down. There are ways around that. So in particular, the plot that I showed was for an Eddington ratio of 3 × 10⁻³ for 1 billion years, which is kind of high for the hot accretion flow case. M87, for example, is more like 10⁻⁵, in which case it would have been a boring straight line. And so I didn't want to plot that. And alternatively, even if on average there are black holes that would be growing at a larger accretion rate like that, a small period of thin disk accretion where the equilibrium spin is 1 again would be able to rejuvenate the spin. So I don't think there's necessarily any inconsistency there.
Okay, yeah, thank you. I just thought that was an interesting connection. Yeah.
It is the case, though, if you want to rejuvenate the spin by accretion, you have to accrete a mass equal to the initial mass of the black hole. So that, we don't see that in these systems. Many of them, it would take a long time to accrete another 10 to the 9 solar masses of material, which is what you would need to spin something back up to maximal spin if it started at 10 to the 9 solar masses.
Thanks, guys. Are there any other? Okay.
I guess just a brief question on your or suggestion for your list of simulations idea. I like the idea. You should probably like split it by scale.
Yeah, yeah.
Because they aren't directly comparable, like small and large scale.
Yeah, that's a good point.
Can we add that? So name of the simulation, reference paper, pros, cons, and scale. Yeah, we could definitely incorporate that. Thank you. I'll write it in the channel as well to make it clear.
Just as a suggestion, maybe having a Google Drive with these inputs you are looking for rather than Slack, we may repeat the same information again and again. So that might help if everyone is able to comment, to edit.
Yeah, I was thinking that repeating is actually might be a good idea because maybe some pros that somebody mentions and somebody else mentions another pro. So I was going to compile everything together. If not Google Doc, yeah, we can move it to Google Doc too. Yeah.
All right, anything else? Do you?
I just wanted to say something I think Brian brought up, which is probing the outflow properties. I'm particularly, one of the concerns I always have with the emission is that because the emission is always dominated by the densities, but it is proportional to density squared, so it's a probe of the denser gas in the outflow, not necessarily the energy containing part. So I was just wondering if you had thoughts on promising avenues for trying to measure and detect and measure the dominant energy component parts, if those are not already. Yeah.
Thing that comes to mind, I would have to think about it. There are some absorption, right, studies that are coming out more and more that show that there's gas infalling towards the core, but it's like using the backlight of the AGN, so it's just a line of sight. Let me think about it. Yeah.
Well, I guess my question is whether those parts that you can see are correlated at all with that kind of energy carrying.
Yeah, I think that's a really good question. I mean, it's
maybe simulations can
something we could ask the simulations. As far as I know,
Yeah.
that hasn't been asked of the simulations.
Are there any other points, questions, comments, concerns? No? Okay. Let's thank speakers again. All right, so room 3 was empty. There's no long-term possibility for this field. So room 2 was large-scale numerics. Who was the speaker for that room? Oh yeah, you were the facilitator. Did you? Oh, you were also the speaker. Okay.
Well, thanks for all the volunteers from our group. I might just do it from here. Is that all right? I don't know. So we talked about quite a lot of things in our room, but I'm trying to summarize them into about 5-ish points. The first one was, but this was all about modeling in kind of probably tens to hundreds of megaparsec scale simulations with resolutions of, at best, 10 to the 4 solar masses, more realistically 10 to the 6 or even lower in galaxy clusters. So the first question was, do we need cosmic rays? And if we do, how do we put them in? And I think this is quite uncertain. Modeling cosmic rays is very uncertain. A lot of the parameters that go into these models are largely unconstrained. And so I don't think we came up with an answer to this one, but how do we test models that we have with cosmic rays in is a question that we didn't especially have an answer for that quickly. In terms of accretion and feedback, we would like to calibrate from small scale simulations. This has started to be done in for star formation and this kind of things. So in small scale, in this case being GRMHD simulations. But do these simulations cover the parameter space that we would need to be able to put them into a cosmological simulation, for example, because we have black hole masses ranging over 5 orders of magnitude. The accretion rates onto them are very different, and will obviously be the interplay with the feedback itself will be tricky. And so it's unclear whether there are enough currently. And we were coming up with like discussing like a wish list for GRMHD simulations almost, or maybe it's not just a wish list, but what we can offer as kind of external boundary conditions, if that's feasible to link those two together, from the kind of thing that Daniel was talking about, and the really like resolved down to the smallest scales that we can manage in a cosmological simulation anyway. And the other thing of GRMHD simulations is that we noted that a lot of the discussion is often around low Eddington fraction accretion and jet launching, and there are a lot less that we were aware of, at least at high Eddington fractions. And so the actual GRMHD simulations, what quasar mode feedback looks like in those is less clear, we were discussing. And coming to the modes, currently in a few of the state-of-the-art, I'm by no means an expert on all of them, but in a few of the state-of-the-art simulations, there are often 2 modes of feedback, and the transition between them can be quite sharp. Particularly, this is notable in TNG, that basically when black holes hit 10 to the 8 solar masses, they go boom because they get forced into the kinetic mode and they quench very rapidly. And in Simba, they only activate their powerful radio mode jet feedback for black hole masses above 10 to the 7.5, or some vaguely similar number, I can't remember exactly. Now, this probably shouldn't be the case. A kind of smoother transition between them would be more interesting. And I guess a question we asked are, can you have, and I think Phil Julie might have thoughts on this, but can you have winds and jets at the same time? And that's not something that exists in cosmological simulations currently. How you'd implement that is another question entirely, but that's not really thought of at all currently. It's a very binary switch. And related to that is that the radio mode that kicks in suddenly and causes this sudden transition is very powerful in Illustris and TNG and Simba as kind of 3 of the flagship models. Is that because they actually should be powerful, or is it because the black holes have been under-regulated by a quasar mode feedback? This kind of higher accretion rate mode, if you have this to be more effective, and that's partly what Marion was talking about earlier, if you have this to be more effective, then you might alleviate some of the need for this very strong feedback later on. And kind of this sharp transition might go away a bit more naturally in that case. And the final point also related to this is we have the choice to inject kinetic and thermal energy in what proportion you can decide based on whatever model you like, but where to put that is a choice that is not simple. So we were discussing how Illustris TNG injects, kicks cells, gives them a momentum kick for stuff that's very close to the black hole already. It's a very local injection of feedback energy. And this kind of blows little holes in the middle of galaxies, which we don't particularly observe in cold gas distributions. But it does quench galaxies effectively. This is true. If you look at then the radio, this is primarily the radio mode I'm thinking of currently, but if you look at Simba, that injects energy at very large scales, and we saw that effect when we were talking about the low redshift Lyman alpha forest yesterday. And you can see the effect on the matter power spectrum is likely to be much larger at that point, and you're heating the IGM up to a very high temperature. I suspect the more correct answer is somewhere in between those two, but the correct way of modeling that is unclear, and what drives this choice between where this energy is injected, potentially linked to the properties of the host galaxy or the region around the black hole. But it's quite unclear where we put the energy, even once we've decided what energy and how much of it. I think that's a rough summary of our points that we discussed.
Nice, thank you. I'd just like to use the microphone privilege and say, look at my paper in October of this year, where I did include a jet and a wind together in the low Eddington accretion mode.
In my defense, my archive catch-up's on about August, so.
Okay, I'm like a year behind. Are there any questions, Julie?
I can comment on the winds and jets. So there are a couple of examples where we do see radio jets, so radio mode feedback in a cluster, but where the AGN is accreting at quite high rates, and we also see a wind. So Phoenix is the classic example. And the way, at least many people in my field tend to see it is, there's a plot that Eugene Churizov made in 2005, if I remember correctly, I think it was 2005, where he kind of plots the power that comes out of a black hole as a function of the accretion rate, okay? And as you start at low Eddington rates, and as the accretion rate goes up, the power is dominated by the radio jets, and it increases, but eventually it's when you reach about 1% of Eddington, it's the power in the form of winds and radiation that dominates. But there is a transition, right? You can still have radio and winds. And so for me, it's always been like a continuous evolution.
I think I was thinking of you when we talked about this particularly.
Are there any other comments or questions?
Yeah, on the question of should these jet mode AGN be as strong as they are in the simulations, I'm wondering if there's a simple way to answer that observationally. It's easy to just sum up the amount of feedback that came out of a given black hole. And then on the observational end, I think we have the amount of energy required to inflate these cavities. So has somebody just done the comparison? Do these numbers actually line up?
Not off the top of my head, but I'm not sure if someone else could jump.
We want to do this. So I have a PhD student who's going to compare, like, physically, does it look like what we see in observations, but also where is the energy dumped, and does it match what we observe?
Awesome.
Thank you.
Any other questions? No? Okay, let's thank Jake. All right, and now room 1, open science. Speaker, come up here. Great, thanks.
So if you haven't noticed, we have a little poll. So if you just want to take a minute and scan it and fill it out, it's just one question.
Oh, there's 2? Okay.
What data?
Okay, sorry. We're gonna do. Should we reveal this poll and then do the second one?
Yeah.
Okay. All right.
Let's do the, maybe we thought the second one might be more controversial.
Do I reveal here? How do I
People
reveal?
had a chance to vote.
24.
We have 24. That's pretty good.
Let's let it go.
All right. Last chance. Get it in now.
26. Oh my God.
We should say this is anonymous. So.
Can you maybe just introduce like data, simulation data, like
So yeah, so here, I guess, right, we meant, sorry, that should have been clear. Yeah, we meant simulation data. So data that comes out of simulation. So, but it looks like we're 90% yes, 10% no. Okay. And then we also wanted to ask. What? Oh, okay. Once we clarified simulation data,
No.
people turned against us. Do we want to do the next?
You mean misinformation?
Okay, that's close now. All right. But we do have the second one.
Yeah, so we also wanted to ask a similar question, should code be public? So, we asked if the data coming out of code should be public, but should code be public? And, we mostly mean, these different codes that we've been talking about. Yeah, well, we can clarify, and we'll talk more about when do you make codes public, which is something we discussed. All right, yeah, I think we should do. Okay, so I think that's slightly more people vote no for this one. Yeah. So maybe I'll tell you the thoughts that we kind of discussed about this, and then we can open it up for people who might say yes or people who might say no. Yeah, so right, we were talking about whether code and data should be public and how we could go about doing that. So first we talked about code. And we discussed that there are multiple ways that you can make code public. So there's just putting it open source, but then there's also these community-based codes, right? So Enzo is a community code. And we talked about some of the difficulties of having open code is it's a lot more work, right? Because you have to maintain it, especially if it's community-based, then you have to make sure that everyone's branches are compatible with each other. And you also, have to document the code much better and probably respond to emails for bug fixes or people wanting help with their code. And, all of this can be time consuming, and it's unclear whether this, this labor is repaid. Also, you could get scooped if you have this nice code that does something, and anyone can access it. They can do the next project you were planning to use the code for. And then finally, there's some worry about, if your code has bugs and it's public and other people find them, while that's good for the community, it's could be very embarrassing, or you could be shamed for that. So that could be a consequence. So that's, but we do think that there are positives to having an open code, right? You're a lot more likely to get more collaborators. You're a lot more likely to get other people who use the code, and it's good exposure. So then we also talked about the data side. And so the data side, we talked a lot about YT, which is a good resource because it can read in data from most codes, although it's not always easy and transparent to use. But they also have a YT Slack, which is useful for interactions and a quick response time for questions. But the biggest trouble with making data public is storing the data. And in the US, we don't have a national database, but would the government be willing to host something like this for us? I think there's been a joke going around if we say that it's so that we can use AI to learn these codes, we need to store them all together, apparently. But we also talked about other strategies. For example, if everyone continues to store their data locally, well, wherever they're running their code, can we have a Globus-like system where, we can have access to everybody's code where it's stored locally if they're willing to make it public? So we also talked about, and this goes for the code itself as well. Do you have some sort of proprietary period on your data? Does it correspond to, once you publish the data, it should be public? So I think these are most of the things we talked about. Again, with the data, with the code, it's mostly a politics problem of are you willing to maintain it? Are you willing to make it public? But the data, while those problems also exist, I think the biggest problem is how is this feasible? And so, we talked about questions about like how much would it cost to do this and things like that. So anyway, I guess we can open it up to discussion, other people's thoughts on should we make things public, whether code or data, and how?
Go first. You're closest.
I guess I'd be intrigued to see what the poll result is if you ask, is your code public or is your data public?
I mean, we definitely we definitely did talk through, right, some of the various codes that we've discussed so far here. We discussed how Athena++, Athena K is public but has private branches, mostly due to management of putting them all together. And so we said as community, Swift is an open code. A lot of parts of Gadget are open, but certain parts of it are closed. Illustrious is a closed code. Yeah, so we did run through a few of them, but yeah.
Any other questions while we wait for Sophie to set up this next one?
Yes.
Oh yeah, go ahead.
Yeah, I guess I wanted to, I had put a couple comments in the Google Doc for the open science stuff, but I actually think that, data sharing is not as far off as we think it is, because there's a lot of things that you can do to reduce the amount of data you have. You can reduce the precision, you can use lossy compression, like the amount of data, or sort of the quality of data you need for analysis is like way smaller, way less than what you need to actually run the simulations. But also like the NSF is going to be adopting the same data sharing mandates that NIH currently has, like in the next couple of years. And so, and NASA too. And so like our primary funding sources are going to require this. And so I think, like there are ways to store data and make it publicly available now. You can put it on Ranch at TAC, for example, and it's like open on Globus and anybody can get it. The problem with it is that it's like there's zero discoverability and there are zero standards. And so like I don't know, like I think that the tapes to store this stuff are out there, but the kind of community self-organization to make it so that it's like discoverable is the problem. I'm not volunteering, but if somebody's interested, I have one.
Yeah.
I'm not volunteering either.
There's another question. That's this back.
So one question related to this is, what do you mean by public data? So I mean, right now in the LISA community, LISA gravitational waves, we are discussing exactly this. So what are, you have different levels. L0 is the output. So what we would call, the raw outputs of the simulations. And you get all the way to L3, which is, a catalog with science interpretation. So I think that what we would call L0 in LIGO, Virgo, or LISA is probably not feasible just in terms of storage space. But then we have to decide at which point we stop. I mean, catalogs are kind of not super difficult to create. They contain a lot of information, but you cannot create something that is not there already. On the other hand, if you want to have the outputs, just think of the difference between galaxy outputs and the black hole outputs that usually for cosmological simulations are at much finer time steps. I don't think that we can put out all the black hole information that we have from cosmological simulations on any reasonable time scale. The other thing is human resources. I mean, this is really, really, really time consuming for people who should be also doing research, not only public service.
Another point.
So about what could be potential platforms for this? I think I'm skipping a couple topics that were brought up after this question, but so I'm sorry. But so ADS, but I was wondering what people think about this, which is where currently we all post our papers. I was actually shortlisted for a job when I made this proposition, but then I took another job. But like I was proposing that ADS could be also used as like a landing site for code, because so essentially, because they're really pushing for open science, and they have a lot of expertise with managing extremely large databases and having really good accessibility and making things really searchable and accessible. So I wonder, like, I think we should like try to build on existing platforms, especially ones that have plenty of financial support already. Like NASA is investing a lot in ADS and expanding it, and like as of right now. And so, yeah, a thought.
Are there any other thoughts? Okay.
I would like to add to the point of public data in general that especially codes that are basically countries and people that doesn't have the resources, that don't have the resources like some of us do, that the minimal thing that they could have is some public database that they can do search and science. I think this can benefit a lot of those communities outside of the US, within the US, etc.
Yeah, I think that's a good idea. But then that, you know, if the US, right, if the government hosts this storage, do they make it available to the international community, or does it become, you know, a US based proprietary? So
Well, we already make MAST available, right?
yeah, sure.
This would be cheaper than MAST.
Any other questions or comments?
I mean, this came up after our discussion, but you know, it's not a new idea, but I mean, we're doing almost the same types of things like subgrid models and different types of implementations. But what about a common library for, you know, AGN feedback or any type of subgrid models, right? You have some input with a lot of parameters, right? Because the input can be moving mesh, particle, or fixed grid. And then you have an output, how it affects, or how the particle changes, or how the grid changes. So that's, and then we all kind of, whoever wants to opt in, then you all kind of work together. So you don't have to kind of reinvent the wheel all the time and everyone's different codes. So, I mean, John, Reagan, and I were just discussing that after our little breakout groups. I don't know if anyone has any thoughts on that or. Just an idea.
Right, but you're talking about like the models, like the code of the models themselves.
Yeah,
Or-
yeah.
Right,
Like
okay.
you can turn on a switch and you can use somebody's model, or
Right.
everyone is free to.
But a switch into what?
I don't know, like an argument like passed into a function
Right, okay,
and to API. So
okay. But I mean, like, in what though? Like you can, oh,
Be a
for like,
standalone
oh,
of
you're
the
talking about
library.
kind of like unit tests almost, right? Or something like that?
I don't know, it would be like its own library that you would
Yeah.
link in,
Mhm.
and then you can call those routines.
Right.
You can actually use.
Oh, I
them
see what you're
models.
saying. Yeah, just for input output, right?
Right,
Okay,
right.
I see.
Because there's Grackle, right? That's to do like, you know, chemistry and cooling.
I think Greg wanted to respond to that.
Yeah, but you can think about the same thing. I mean, Grackle is a library for chemistry and cooling, but you can do the same thing for subgrid models or any type of models.
Yeah, first of all, I just want to, I think that's a great idea. In fact, I think there's sort of two dimensions there, right? Because there's the model, right? That is the physical description of the model, and then there's the actual implementation. And one could imagine implementing the same model in different codes. And I'm thinking of the great work that the Agora collaboration has done here. Or implementing different models in one code. I think these are both useful things which has not been explored significantly in the community to date. I know there are some efforts along those lines. And I just want to encourage them because I think we learn a lot by doing experiments like that.
Yes, I was trying to remember a thing that I could not find on the time, but Australia has this site called Tau, theoretical, and I can't remember the rest, but they host SAGE semi-analytic model run on different Millennium Bolshoi and so on is publicly available. I think this is kind of like a input-output thing that you were discussing, right? So that's Australia given free access to public data with, I guess people have still like a maximum of 10 gigabytes of storage there, and then you have to get out, but that's the concept.
Any other points? Yeah.
Thanks, Doug. Yeah, just to follow up on what Greg was saying and what John had said, I think that would be a good project for as a community to take on. Like, and Greg is right. You could just put it into one code initially to download the effort, to downplay the effort a little bit, and have multiple models in that, and get it to run in a similar way that Grackle does. And Grackle is pretty, ubiquitous. It doesn't need to serve every code initially, but as a starting point, I think it could be a really good project for the community to have a go at, and without being totally intractable.
All right. Any other comments, questions? I did some of the work of putting Simba into Swift as well. So that has Eagle and Simba completely as described in the paper, at least. The models, yeah. And even then, it's still not as easy as it seems, just because of the code itself. It gets really, you really realize how much the architecture makes a difference. And that's like the implementation versus model issue. It really can make the model act in a way that wasn't intended originally, or it might not even work.
This is true, but Grackle at least does, is a precedent for doing these things. It's somewhat code agnostic.
Agnostic, yeah. As long as you can have the same inputs.
Yeah, absolutely. You have to have an API.
Yeah.
Right, which you sit into.
Right.
But you have to set it up so that it, whatever your model was, could fit inside that API. Right? Otherwise, it doesn't work.
Any other questions or comments? Okay, well, let's thank Amy and all of the speakers. And that's it for today. So thank you all for coming. We'll see you tomorrow.